Okay, I want to just try to explain some of the issues with resonance. So I'm going to try some technology for capturing this. The video will not be very big, but it's the best I can do on this. So I'm going to one of these problems that you referred to involving resonance. And with these two different images for the same thing, the point is that the real thing is neither a structure in which the bottom oxygen is full negative charge with a single bond which is weak, and the top oxygen is double bond, short and strong and uncharged. Neither is the reality that the top oxygen is all negative and the bottom oxygen has no charge. In reality, the real species is an average of these two images. So in the real thing, the top oxygen is the average between no charge and one charge. It's half minus. And the bottom oxygen is half minus. Each bond averages out to be really 1.5. Now, one of the things that we observe between these resonance structures is that the only thing that differs between the two images is where electrons are located. So when I compare the bottom figure to the upper figure, what is happening is that two electrons are moving. So instead of the right oxygen having 3 lone pairs, he ends up with 2. Those 2 electrons are now found as a double bond to the nitrogen, and 2 electrons that are originally imaged as if they were in a shared bond end up being relocated onto the top oxygen, which now has 3 lone pairs and a single bond. So it's on page 6. I talk about some of these issues in more detail, but a key is that the actual species is a hybrid of the actual resonance form. So neither of the two pictures provides an accurate depiction of the real molecule, but the average of the two pictures in this case do a better job. One of the keys that I emphasized in point 4 is trying to recognize when two structures are or are not resonance structures. If there are two pictures, are they really resonance structures where the only thing that's moved are electrons, or are they actually completely different molecules where we have moved hydrogens? The point number 5 is that the only thing that changes is the location of the electrons and of the charge. But this is a big deal because we're going to see a lot of structures as the semester goes by in which resonance would apply. And if resonance does apply, that changes the stability. So something which is more stable will form more easily. Something which is more energy stable will be more content and will react less aggressively. You can't really read these because my image is so small, but point number 7 is the word allylic. And not all resonance structures involve the allylic scenario, but the most common that we will see does or do. And an allylic situation involves 3 atoms, 2 of which are double bonded, but the third will have either a plus charge or usually a minus charge. And when you have these allylic type situations, you can actually redraw the same molecule, by relocating the double bond in the other direction among the three and putting the charge on the other end of the three. Okay? Very, very significant situation. So then we were trying to look at some resonance situations in number 2 and on page 7 and try to imagine, you know, how the electrons might be relocating between one image and the other. So in case 2, both of these are allylic. But let me take case 2a. Oops. So in the first picture, it looks like this. In the second image, it looks different. In the second image, the double bond is to the right rather than to the left, and the plus charge is on the first carbon rather than the third carbon. We want to be able to envision how electrons are repositioning themselves. So essentially it's the 2 electrons in the pi bond that are in a different place. So if I take them where they were in the first picture and show them moving over to the right carbon, now the right carbon will be seeing those 2 electrons. But if those 2 electrons move from between the second and the first carbon and end up being located between the second and the third carbon, now the first carbon ends up not seeing them and is electron poor. Conversely, if we have a negative charge, so in case 2b, we had a negative charge initially on the right oxygen with the left oxygen double bonded, but there's no reason why the middle carbon needs to be double bonded to the, oops, what happened there? Let me do this one again. So in the first image, the right oxygen is negative, the left oxygen is neutral. An alternative would be to have drawn the right oxygen as neutral and the left oxygen as negative. How are electrons relocating themselves? To change, if 2 electrons that were shared between the second and the left carbon actually stop being shared and move on to the left oxygen, that oxygen will change from originally having 2 lone pairs, now following, you know, if I account for those electrons with that arrow, that's suggesting that now that oxygen will have 3 lone pairs. The original right oxygen, negative oxygen, would have had 3 lone pairs, but in the right image it has 2. So, you know, using our counting process, if I say those 2 electrons moved and one of those lone pair electrons is now shared rather than unshared, that kind of tracks the electron movement to see how they're moving from the first image to provide the second image. I think you asked about which of 2 resonance structures is more stable. That's what's happening in question 3, and there were some guidelines for comparing stability. So that was in point 9 on the previous page. If there's 2 images for the same, you know, 2 resonance structures, are they always, is the real hybrid always going to be a 50-50 blend of the 2? Is it going to be the average of the 2 pictures? And the answer is no. Sometimes one picture is better than the other, and the real species is more like one of the 2 resonance structures than it is like the other. So the guidelines were twofold. How many bonds do you have? If you've got more bonds within the constraints of electronegativity, you're more stable. The second, if two images have the same number of bonds, but charge is in a better place, we'd rather put the charge in a better place. So in case A on page 7, between these two images, the left image has an extra bond. So with more bonds, the left image is more stable. So the real molecule is closer to having a double bond than to having a single bond. There's some negative charge on oxygen, but not a lot. In the second image, again, the left image has double bond, the right image has single bond. The real thing is going to be more like the left image because that has more bonds and it's not violating octet rule or anything like that. Case C is an example of an allylic case. In the one picture, the negative charge is on a carbon. In the other picture, the negative charge is on oxygen. The number of bonds are the same. So it's not like one is making a more than 50% contribution to the hybrid than the other. Which makes a, I don't think I said that right. It's not like the two are going to make equal 50-50 contributions to the hybrid. So is the real species more like the right image or more like the left image? Well, it's actually more like the right image because you'd rather have more negative charge on oxygen than you would on carbon. So electronegativity issue kind of guides you in evaluating which is more stable. So again, when you have resonance, particularly in the case of allylic things, if I'd have a negative on an oxygen versus on a carbon, the species with a negative on oxygen is going to be somewhat better. So the real thing is not going to be 50-50 sharing of the charge between the O and the C. The O is going to have more of it. Not sure how helpful this is, but I'm doing my best. Good luck and get in touch to follow up.